I am Pavitra Varsha, student of IIT Madras. As a part of my coursework, I am going to present to you basics of photonics. By the end of this lectures, you can understand or get to know the basic terminologies and basics of photonics and science behind the photonics. The foundation of photonics starts from wave optics, which is light theory, which is evolved by wave optics, followed by electromagnetic optics, followed by photonic optics. And photonic optics. We'll go through one by one and look into the basics of each of the theory. At the end, we will have a basic understanding of photonics in whole. Ray optics, as the name suggests, in ray optics, light is considered as a ray, that is, light travels in a straight line. Light is considered as a vector. Ray optics is the simplest theory of light. Light is described by rays that travel in different optical medium in accordance with the set of geometric rules. Ray optics is therefore also called as geometrical optics. Through ray optics, we see why different objects emit different colors. The loss of reflection, refraction, and also helps us to understand the propagation of light through optical fibers, which is now a breakthrough technology in the optical domain. Here we can see the loss of reflection, the reflected light and the reflected ray. Incident ray lies in the same plane and they both make same angle with the normal. These both are the loss of reflection. Loss of refraction, this refraction occurs at the boundary between two medias. At the boundary between the two media with the two different refractive indices, N1 and N2, an incident ray is split into two, reflected ray and a refracted ray. The property of reflection and refraction gives rise to total internal reflection, which is the main working principle of fiber optics. Simple optical components. There are few optical components which uses reflection properties of various here we see a planar mirror. A planar mirror reflects the light originating from this object such that the reflected rays appear to have originated from a point behind the mirror called image, which is equal distance from the mirror. Typical household mirror holds planar mirrors. What is the use of this optical components? Let's say I want my light to fall. So there I can change the source or direction of the light source or change the mirror. By exploiting the ray theory, here we concentrate on changing the kind of mirrors. Next is paraboidal mirror. The surface of the mirror is parabola in shape. It has the useful property of focusing all the incident rays parallel to the axis to a single point called focus, similar to the top paraboidal antenna. Here, the paraboidal mirrors have a focusing property. Since they are focusing at a single point, they can be used as in flash lamps and telescopes. Elliptical mirrors reflect the rays emitted from one of its focal point to the other. Here, the elliptical mirrors in the elliptical mirrors, light undergoes a phenomenon called Hero's principle, which states that the light undergoing a reflection from a plane surface will follow the path of least distance. Elliptical mirrors have imaging properties because they can focus light from one focal point to the other focal point. They are usually suitable for as bathroom mirrors and decorative wall mirrors. Let's say if we put a light source at one focal point, it is possible to collect the light at the other focal point. These are also used to incident light in light of the lamp into optical fiber or a light guide. Spherical mirrors, however, they have neither focusing property or nor imaging property, but they are easy to fabricate. Then when using under paroxial approximation, parallel rays which are very close to the axis, they can be considered for they exhibit both focusing and imaging properties. There are two types of spherical mirrors, which are concave, which are used for dental applications, and convex, which are used in parking slots. A ray transfer matrix is transfer matrix in which an optical system is a set of optical components placed between two transfer planes, let's say Z1 and Z2, referred to as input and output planes respectively. The system is characterized completely by its effect on the incoming ray of arbitrary position and direction, that is y1 and theta1. It steers the ray so that it has a new position and direction y2 and theta2 at the output plane. The ray transfer matrix is the result of linear algebraic equation from the position and the angle of the ray or at the input and output of the planes. From this ray transfer matrix, we can understand how the light ray is undergoing changes in an optical system. Total internal reflection. Total internal reflection is nothing but when a light ray is incidented at an angle greater than critical angle. What is critical angle? Critical angle is something when a light ray is incidented at critical angle, the refracted ray grazes the interface of two mediums. That is called a critical angle. So when total internal reflection is nothing but when the incidented angle is greater than critical angle, the light ray is completely refracted back into the same medium of the incidence. This is the basics of fiber optics. When eta 1 is greater than eta 1 is greater than eta 2, internal reflection happens. This total internal reflection happens when eta 1 is less than eta 2, Snell's law cannot be satisfied. This phenomenon of total internal reflection is the basis of many optical devices and systems, such as reflecting prisms and optical fibers. The light rays incidented in an optical fiber, light rays incidented on the core and cladding, where core has higher refractive index than cladding, greater than the critical angle, undergo total internal reflection and are guided to the fiber without refraction into the cladding. Here we can see that a single mode fiber core, this is the basic structure of fiber optics. Through total internal reflection technology, we can guide light through this core. Remarkable technologies that advances in the fabrication of optical fibers over the past 2 decades allow light to be guided through 1 kilometer of glass fiber with a low loss as 0.2 dB per kilometer. Numerical aperture is light gathering capability of fiber, that is the range of angles at which light can be coupled to the fibers such that the light undergoes total internal reflection inside the fiber. Is decided by numerical aperture. This is the derivation of the total numerical aperture. Here you can see that let's say incident angle is greater than critical angle. For a acceptance angle, that means angle at which the light is incidented from the outer medium to the fiber. The acceptance angle theta A is sine inverse of numerical aperture. Here for this derivation, we have considered the medium surrounding the fiber A with refractive index n is equals to 1. Attenuation. Attenuation can happen due to reflection, scattering, absorption in the fibers, which causes the light ray to attenuate at certain wavelengths. At first, fibers were used at 1850 nanometer because of the support of the equipment and low UV absorption. Now we use 1550 nanometer because of overall low absorption, considering both infrared OH absorption and Rayleigh scattering. This absorption phenomenon, the light with absorbing certain wavelengths at for a particular materials. This absorption phenomenon is used as which is a wavelength dependent, is used to absorb the is used to identify the kind of materials which are being used. Here we can see at the 1.4 micrometer, OH absorption is pretty high. That is the reason why the water vapor which has OH ions very absorbs the light ray. I mean, any communication doesn't have 1.4, wireless communication doesn't have 1.4 because water vapor in the atmosphere absorbs the waves or absorbs the electromagnetic radiations. Optical waveguide is used to trap the light in a medium. They are used for transmission of light, modulation of light. Photonic integrated circuits make use of these waveguides to create an optical chip. These waveguides work under the principle of total internal effect. The different kinds of waveguides that you can see in an integrated circuit format. Modes and by fiber V parameter. The modes, the number of modes, the number of ways a wave can a ray can travel inside the fiber is depending upon the geometry of the fiber, refractive index of the core and cladding, numerical aperture, and wavelength of the incident rays. The step index has a uniform distribution, a gradient index has a Gaussian distribution. When the core diameter is small, only a single mode is transmitted and the fiber is said to be single mode fiber. That means the light travels, doesn't undergo any total internal reflection. It goes in a straight line. Fiber with larger core diameters are multimode fibers where total internal reflection takes place. The mode of the fiber differs with respect to the wavelength of the transmission. For few wavelengths, a fiber can be a single mode or a multi-mode. Let's say if the wavelength increases, the number of the kind of mode, whether it is going to be a single mode or multi-mode for a particular way, for a particular fiber also changes. V is an important parameter that governs the number of modes and their propagation constant. It depends upon the diameter, wavelength, and numerical aperture. For a single mode, the V number should be less than 2.405, which allows the fundamental linear polarization mode to travel into this. The total number of modes in a fiber depends upon the V number. In this equation, we see the relation between the modes and the V number. Modal dispersion. So when light can travel two ways in a fiber, where it goes in a straight line. Second, it undergoes total internal reflections and it travels a longer distance compared to the straight line the light traveling in a straight line. Due to this, the ray which is undergoing total internal reflection reaches the fiber slower than the the light ray traveling in a straight line. Due to this, even though they are of same frequencies, there is a delay between the modes. Even though they are both starting at the same time, there is a delay between the arrival of the waves. Because of this phenomenon, we can see there is a spread in the frequencies. In single mode, there is no dispersion, whereas in multi-mode, we can see there is a pulse broadening. This kind of difficulties with the propagation of light in a multi-mode fiber arises from the differences among the group velocities of the modes, as group velocity is the velocity at which the entire information is transmitting. Since each wavelength undergoes different timings, arrive at different timings, the velocities also changes. The spread is called modal dispersion. Vision of fiber optics is communication systems as they offer very high data rates, and they are also used in medical applications like endoscopy and virus detection. The drawbacks of ray optics is that it fails to explain the phenomenon of diffraction and interference. It is only applicable for objects having dimensions larger than the wavelengths.